Okay, let's get started. Hopefully everyone had a good break. Let's get back to it. So just to give a roadmap, get our heads back into where we're at. We're going through Homework 3 content. We're roughly halfway through Homework 3 content in the fact that it's WebSockets and WebRTC. We did all the WebSocket stuff, though I will talk about some WebSocket stuff today. So we did cover everything that you need for WebSockets. So learning objectives 1 and 2, that's just WebSockets. You don't have to do any WebRTC if you're just trying to pass the course by design. And WebSocket features. We covered everything I need to talk about for application objective 1. You can do everything with WebSockets for the homework. And then this week we're going to learn how to do WebRTC. This is going to create a video chat, a peer-to-peer video chat between two users. And then application objective 3, the TAs are excited that I added this one, making a Zoom clone. Making a true peer-to-peer Zoom clone. That's our goal for WebRTC. And I should probably just do the demo right away just to show what we're talking about. I'll do more demos throughout the week, but especially Friday. But if I go to localhost 8000 / WebRTC, right? Oh my goodness. My browser's been doing this to me, and it's really not cool. Localhost 8000 / WebRTC, not as a Google search. Oh, I did 8080 that time. Not as a Google search. That's the number one recommendation whenever I try to go to my own website is to search that. No, I want to actually go to that URL. And there's my video. I forgot I have it setting up right away. I'm going to open another tab. Not a Google search. I almost did it again. I'm going to open up. Do it this way. And I have to mute these or else it's going to be really annoying. And now I'm in a meeting with myself all 3 times. Obviously, it's only one camera attached to my laptop right now, so we're all the same person. Actually, we get 4. I open them up in a strange order there. But this is our ultimate goal for application objective 3, is to have effectively a Zoom clone that's all strictly peer-to-peer. That's what we want to do. That's how it works. Let me keep that mute. Actually, let me just close it. So that's what we want to do for application objective 3, for those of you getting that far. Yeah. Of course. All right, we'll talk about that during grading. I'm talking about WebRTC. That's what you raised your hand for in the middle of the WebRTC demo? Come on, man. So that's what we want to build. That's what we're working towards. And then we're going to talk about all this week of how to get that to work. Firefox better than Opera? I mean, Firefox is running the Spotify for what it's worth. I think I might start switching over to Firefox. Demo has a sufficient amount of Jesse. You didn't want more? Yeah, Marauder knows what's up. All right, so that's what we want to do. That's what we want to build. So let's talk about what that even is, what this technology is, what it does for us. Today we're going to give an overview of WebRTC, and then honestly I'm going to switch back to WebSockets and do a WebSocket demo that I didn't find time for before break. Wednesday we're going to talk about more details of how to get it done, and Friday is going to be in code and demos the whole day. So let's talk about WebRTC. Oh, let's talk about WebSockets. I want to review WebSockets first. WebSockets was a long time ago, 2 full weeks, well, 1 full week, I guess. So let's talk about WebSockets and just remind ourselves what WebSockets even are. My brain's half on vacation still, and I just did 3 1/16s. We'll get through this, though. We're going to do this. So with WebSockets, the clients send a request to your WebSocket path with the headers connection, upgrade WebSocket, uppercase U, lowercase w, not a typo, and secure WebSocket key, which is some random value. And then you're going to respond with a 101 switching protocols with the same 2 first headers, but your WebSocket accept is going to be this accept response. So the big part of the WebSocket handshake is reading this key and then generating the right accept response. The key is random. It will be different every single time, so you do have to compute the accept. And we do that using this strategy, this protocol, this procedure, I guess. Procedure, I like. You're going to read the key, that random value. You're going to append this exact string, which I always find this a funny part of the WebSocket protocol. You're going to append this exact string to the end of the key. Take the SHA-1 hash of that, and then base 64 encode it, and that's your accept. And this is made to avoid caching. We're going to bust up some caching to make sure that our WebSocket upgrade requests are not cached, because we need to get those requests on our server. We don't need some intermediary server with a caching system caching that and then sending back the response. We can't have that, so this is going to avoid caching because the key is not, at least with high probability, not going to be the same value twice ever. So it will be different requests, so it can't be cached. When we got the packets, we saw packets in this format. So we were parsing at the bit level. At the bit level, the first bit is the fin bit, which is either 0 or 1. 0 if this is not the last frame for a message, and 1 if it is the last frame. 3 reserve bits, which will always be 0 for our purposes. The opt code, which is going to be either 0001 for text, 1000 for closing a connection, and then 0000 if it's a continuation frame. There are a few other ones, ping, pong, binary data that we're not going to use in this class. But those are the 3 that we're going to see that you'll have to code in your homework. A mask bit, which is always 1 when you're receiving a frame from the client, and it's always 0 when you're sending a frame to the client. A 7-bit payload length, which is either going to be the payload length, which is the number of bytes in your payload, very similar to the content length, or if this value is exactly 126, then that means the next 2 bytes are going to be your payload length. And if this value is exactly 127, the next 8 bytes are going to be your payload length. Then if the masking bit is 1, so whenever you're receiving a frame, the next 4 bytes are your masking key. When you're sending frames, the mask bit will be 0. This masking key won't exist, and you'll go directly to payload data. Right after your payload length, your data will be the next thing that you append to your byte array. And then finally, the masked payload data. That's going to be the payload data XORed with the masking key. I kind of went over all that with the visual. Any quick questions on WebSockets before we shift gears to WebRTC? I'm going to do intro slides to WebRTC and then demo some WebSocket stuff that I didn't have time for. So we're kind of sandwiching WebRTC with WebSockets right now. Some of the functions in JavaScript are deprecated. I need more context. Any tips on not making a new username for every message? Cookies. Damn, I'm hungry. Oh my God, same. This is a good conversation. Now I'm hungry too. Damn it. to not making a new username for every message. So in your code, you have your WebSocket handshake code, right? And then after that, you enter an infinite loop where you're constantly, while true or whatever, where you're constantly reading from the WebSocket and treating whatever you read, or reading from the TCP socket and treating whatever you read as WebSocket frames. So when you do the handshake, the way I, for what it's worth, did in my solution, what I recommend, you do the handshake, you generate the username, and then you enter your infinite loop. And then that username is persistent throughout the infinite loop. You have the same username for that user when you're running that code in that stack frame. It's always going to be the same username. And then you enter that frame on a separate thread for each user. So each user is going to have a different username, but it's going to be consistent for them every time they send a message. If you're getting a different username each time, my guess is that you're generating the username inside the infinite loop instead of right before that loop. Cookies will be the solution when we get to homework 4 content, when we have authentication, for what it's worth. And on Edge Stream, that might be client side. Wait, on Edge Stream, bless you. On Edge Stream, when do we even use that? That might be the WebRTC stuff, where we have the on Edge Stream. But usernames, for now, usernames are controlled server side. When we get to authentication, your users will generate their own usernames and passwords, and we'll do all the authentication goodness. For now, they just get random usernames controlled by the server. All right, any other questions? It is WebRTC stuff. Okay. Yeah, I was trying to remember, like, where, I know I just saw that, but I forget in what context it was. Yeah, that's when you're adding either the remote or the local stream to your front end, if I'm not mistaken. Oh, that's the method that was deprecated. Oh, I see what you're saying. On Edge Stream was deprecated in Firefox? Oh, no. Well, I might have to update the JavaScript. I'll look at that after lecture. I'll see what happened with that. As long as it still runs, we'll be able to get through. But if it's actually deprecated and removed, that's something I'll have to fix. Maybe when we go back to the code, I'll try to run it in Firefox and see if it works. We'll try that. I thought I did test it in Firefox, but I probably tested it so long ago that it wasn't deprecated. Anyway, I'll look into it. WebRTC demo we already did. So WebRTC, what is this? What even is WebRTC? So with WebRTC, our goal and what it's going to do is establish a live streaming peer-to-peer connection between two users. And we're going to use it to stream. It's usually for streaming multimedia content. We're going to stream video and audio, which effectively build in the Zoom clone that's strictly peer-to-peer. It's not even going to rely on a server, sort of. If it didn't rely on a server at all, we wouldn't be talking it in a back-end course. But we'll talk all about it, all the details on Wednesday. This is pretty new. So the browsers are adapting it. The major browsers, as long as they're up to date, they'll have WebRTC implemented. But, it's something where if you're deploying it to a live user base, some users might not have an up-to-date browser. Some users don't update their browsers ever, and they might have 5-year-old machines that just don't have WebRTC implemented in them. So something to keep in mind, not for this class or for pet projects or side projects or anything, but when you go out there in the workforce and you're working for a major corporation with millions of live users, probably not a technology you can rely on. That not most users, but a good portion of your user base will just be excluded from the app, and then your IT support is going to get 1 billion phone calls because that feature doesn't work for them, and just a reality that we have to live with. So most users are going to be able to use this tech, but not all users because it's still pretty new. And most of the work, we're going to see WebRTC. I have a lot to talk about in the slides. and a lot of theory to talk about, but most of the actual work is going to be done by your browser. So we don't have to worry about how to actually stream the information. The browser is going to handle all of the details of that. We just have to facilitate the connection, establishing the connection itself. Once the connection is established, the browsers are going to take over and implement RTC, WebRTC. So I'll talk about it for a week in lecture, but when it comes to doing your homework, aside from Application Objective 3, that is a pretty good challenge. But Application Objective 2, just getting WebRTC to work with 2 clients, which is what Application Objective 2 is, not too much work. Mostly because all the front-end code is given to you, and the browser does most of the heavy lifting. So, all right. So WebRTC establishes a live streaming peer-to-peer connection. Let's pick this sentence apart and talk about what each part of that sentence means. Let's start with peer-to-peer. This means that your 2 clients are going to communicate to each other without a server. There's not going to be a server involved. Well, okay, there will be some servers involved. But once the connection is established, a server is going to help you establish that connection. It's going to negotiate terms between the 2 clients. But once the server negotiates that connection, the 2 clients will connect directly. The server steps out of the way. Any servers involved step out of the way. And then it's strictly, purely peer-to-peer. So anybody who likes their privacy, this is the protocol for you. If you want to chat with somebody and not have any server, anybody eavesdropping and seeing what you're talking about, like Zoom or nobody uses Skype anymore, but can't think of another one. But Zoom, I don't know, voice chat on Discord, whatever else you want to use, FaceTime, yeah. It's like the browser's going to prevent the other user from attacking you, but I mean, there's always the potential for vulnerabilities. But you have a lot of potential anyway, even if you're going through a server, if you're getting information from a user. But yeah, there could be more risk here, but I wouldn't be concerned. Like, because they're sending you multimedia, so they'd have to send you like a video. They might send you a video that you don't want to see, for sure. But they would have to send a video or audio that could somehow escape the browser and corrupt things, which possible, but unlikely unless you have a very sophisticated attacker. So I wouldn't be too worried. But yeah, there's no server filtering anything, so you might see something you don't want to see. Just be careful who you talk to. But yeah, there is an amount of trust with the other peer. And keep in mind, your ISP can still see all your data. You're never going to be 100% secure on the internet, or I shouldn't say secure. You can be secure. You're never going to be 100% private on the internet. You are using a lot of infrastructure that's built by a lot of people, organizations. Like, there's a lot of people involved. You're never going to be 100% private. With this, you can get pretty close. Your ISP can see your data, but if you encrypt it, if you encrypt a WebRTC connection, that's pretty damn close to being private. But your ISP can still see who you're chatting with. So you can add a VPN, and I don't know, we can talk about privacy all day, but not what we're talking about today. Actually, it is kind of what we're talking about. If we're talking about WebRTC. So you can each have a VPN, communicate to the VPN, and then have the WebRTC connection go through them. But who's running your VPN, you have to trust them. And even then, if it's encrypted, they can't see what you're doing. They can just know that you have a connection with this other person. If you're both using a VPN, each VPN would know that the other side is a VPN, but they'd have to collaborate to say that these 2 people are communicating. And even then, like, yeah, or Tor. There's a little bit of trust in Tor, but much less so. But with Tor, you could have a rogue node. It's a lot easier for a node to go rogue than a VPN, like an established organization to, is that true even? I don't know. Depends on a lot of your outlook on the world, I guess. If you trust a Tor node, because whoever's running, so I don't want to get too far down this, but it is a fun topic, so we can talk about it. Tor is like a series of VPNs. You go through a whole bunch of VPNs effectively, and then you connect to whatever you're connecting to over the Tor network. So each one of those nodes that's acting like a VPN, it's just like some person who said, yeah, I'm going to be a Tor node. You have no idea who those people are, obviously, because it's all about privacy. You'll never know who they are, much less can you trust them or not. So a Tor node can go rogue and just be there to steal data and whatever. But since there's so many layers, if a Tor node in the middle of that VPN chain, effectively a VPN chain, goes rogue, they can't tell anything. They just know that these two nodes are talking to each other, which doesn't gain them anything. If you have one of the endpoints go rogue, that's a little more scary. They can do a little bit more damage, find out a little bit more information. But do you trust random people who you'll never know who they are more or less than an organization selling a VPN service? That's the question you'd have to ask yourself. At some point, there is trust that you have to give to somebody. If you want to stay 100% private, somebody out there you have to trust. Or set up your own VPN. But, I don't know. But anyway. But WebRTC does cut the server out of the picture. So you don't have to trust a server. And you do get privacy in the sense that they can't see what you're doing. Nobody has access to the information that you're sending, which isn't true. Like if you send a DM on a social media site, you send a DM to somebody, like the server, you are trusting the server. Like they have full access to your data, unencrypted. They have to because they have to handle that information. So do you trust that server? Do you trust that company is a question. With WebRTC, you don't have to trust anyone if you accept the fact that someone out there could know that you're talking to another person and know who both of you are, even if they can't see what you're saying. If it's encrypted, what can the node do? Yeah, so I'm talking about, can they tell if that you're talking to someone else? So if a node sees, if it's an endpoint, if it's the first node that you're connecting to, that node knows that you are accessing a Tor site. They don't know what you're doing, but they know that you are using Tor, which isn't that much information. Usually you can just be happy with that. But are you positive? So there should be, it's called onion routing because there's all those layers, which is what I call the VPN chain. If you're using Tor, have you ever checked to make sure that that is what's happening? Because there could just be one layer. So if an endpoint said, you know what, I'm just the only layer, and it connects you directly to the site that you're accessing, and there's no layers to the onion, it's just one shell, which is just one person in a basement with running a server. Like, how have you ever checked that? Those of you who've used Tor, have you ever checked that? Do you know that it's using a layered onion? So one person goes rogue and says, yep, I'm the only link in this chain. And now they know that you visited shady site on the Tor network, which even then, maybe they can't deduce too much of that. Your information is still encrypted, so they don't know what you've done. But they do know that you visited that one site, potentially. So that's what I mean. It's still not, depends what site you're visiting, I guess. It's still not the biggest concern. But if you're going on the Tor network, you're probably not accessing something completely kosher. Like the fact that they can see what site you visited could cause issues. Yeah. If you use any social media at all and you trust them with your data, you trust everybody with your data. Exactly. Which I always find the privacy conversation kind of strange because most of us just leak our data willingly all the time. Yet we talk about privacy so much in the context of the internet. Most people don't care. Like, I don't care that much about my data. My data can be out there, and it's hard to dox me because I've already doxed myself so many times. Like, people know everything about me. But I still talk about privacy because I know it's an important topic. It's something that people do care about. But anyway, let's get back to it. So peer-to-peer. So privacy takes the server out of the equation. Live streaming. So what we want is real-time streaming data where speed is important. Not necessarily speed. Ping time. I'll just read it from the slide. Delay is the word I'm looking for. Delay is critical. How much lag you have in that connection is of critical importance. Even a very small amount of lag in a video call can be completely critical, can completely break things down. If you've ever been on a video call where you have like a quarter of a second of delay, it's almost unusable. You start talking over each other constantly. Nothing really gets communicated. It's really, really difficult to communicate like that. So we would need to be fast. There's one issue with TCP that we've been using all semester, is it's kind of slow. TCP, every time I talked about TCP, I said we use TCP for reliability. Make sure we get the data that was sent. Nothing in there is related to speed. In fact, it's pretty slow. So if we have a drop packet, we request a resend. We say, okay, you told me I was going to get packets 0 through 500. I'm missing packet 232. Can you resend that one to me? And after a timeout, which the timeout alone is going to be too much time, and then the other side says, oh yeah, sure, here's your missing packet, and then we get the packet, and then we reassemble the data for these 501, because I chose the indices that way, 501 packets, reassemble the data, and then show the data to our user. If that's in a live call, a video chat with somebody, we're not waiting that long. Like that's not how it's going to work. That's not how we can let it work. So this doesn't work for real-time streaming. It's not used for real-time streaming. Before anyone calls me out on it, Twitch, YouTube streaming, YouTube Live, it's not really a real-time streaming service, at least by my definition of it. I mean, we can argue semantics here, but there is quite a bit of delay in both of these services. They do use TCP for their streaming video, and you're always, a few seconds behind the stream. As like if you were in the same room as the streamer, you would notice a few second delay. But usually we don't care because whatever. We're not having a conversation back and forth with the streamer, so we don't need to be right exactly live within milliseconds. But if you're on something like Zoom, you do have to be within milliseconds, a handful of milliseconds of each other, as you are communicating back and forth. So we can't use TCP for live, real-time, like two-way communication, I'll say. If it's a streamer broadcasting, TCP is fine, because you can afford a few second delay. So TCP doesn't do it for us. Enter UDP, something I won't talk about outside of WebRTC and just a few slides. You won't have to code UDP at all for what it's worth. But this is one case where UDP does come into this course. UDP is at the same layer as TCP. It's a layer on top of IP, but it doesn't do anything for reliability. It's pretty much just using raw IP packets. It has a little bit of overhead. It has its own headers and things like that, but it's very lightweight. It's kind of like what WebSockets does with TCP, where WebSockets is pretty much just using the TCP stream with a little bit of overhead, a little bit of structure. UDP is very similar in relation to IP. UDP is very close to just using raw IP packets. It's going to send the packet. If it's dropped, whatever. If it makes it, cool, and that's it. So when we're streaming video and we drop a packet, we don't care about going back to that packet. We're just going to miss a little bit of data in the stream, and that's it, and move on with our lives. It's okay. You saw the person, they were talking, then they froze for a quarter of a second, and then they started moving again. We had a drop packet, and it's no big deal. Or any number of things could have went wrong with that. But we just move on. We don't need to go back and get that information. If we do, we'll just ask the human to repeat themselves. We don't need to slow down and increase our lag time to make sure that we get every single piece of information that was sent. So UDP, send the packets and accept the losses. So WebRTC works over UDP. Same with Skype used to. I think Skype's just dead, right? But Zoom now will use the same thing. I never even checked if Zoom does, but I'm sure it does. It kind of has to. Can't use TCP if you have two-way video communication like that. And servers are still involved. So that's our peer-to-peer live streaming. There are still servers involved. There's actually 3 types of servers that we're going to talk about. One of them we're only briefly going to mention on Wednesday and today, I guess. So let's talk about these 3 servers. One, the signaling server. This is the most important one for CSE 3.12 because this is the one that you'll implement. The other 2 servers we're not going to implement. This is the server that you're going to use, that you're going to write. This is going to pass messages between the clients. So when clients want to connect to each other, the client's going to connect to your server and say, boy, I'd really like to join that video call. And then your server is going to go to the other users and say, hey, this person would like to join the video call. And they're going to respond like, yeah, I'll join the video. They can join the video call and then send back. And just facilitating the messages. Because clients can't just talk to each other. They could, right? But do you know your friend's IP address, especially as it's changing, as they're moving around a network, or they drive home and they're on a different network entirely? Do you always keep tabs on what their IP address is? Probably not. What about what port numbers are available for them to use? Probably not. So we need a signaling server to communicate that information of what port, what IP address are the 2 important things, most important things. And then we also negotiate what protocols they're going to use. When they're streaming video, what's the bit rate going to be? So they can interpret those bytes as they're being sent over UDP packets. They need to be able to interpret those bytes as audio and video data. So is this going to be a video-only stream? Is there audio attached to it? All those things have to be negotiated. A good thing for us on our signaling server is the client's going to generate all that stuff, send it to us, and we just send it to the other person. We don't actually have to interpret the WebRTC messages at all. We just have to make sure that the messages get to the right spot of where they're going. So that's our job. We're going to basically be a messenger. We're going to send messages between clients so the clients can negotiate those connections and establish those connections to each other. A stun server, we will need this server as well. Session, I always have to look at the acronym, I never remember. Session Traversal Utilities for NAT server. This is going to tell clients what their public IP and port are. So you usually can't see what your IP and port number are directly. You can look up your IP address, and most of the time you'll get depending on how you're looking at it, you're going to get your local IP address, which is usually behind a NAT, a network address translator. And then the NAT, whenever you want to talk to the outside world, is going to use its IP address and whatever port it chooses, which will be your public IP address and whatever port it has available that it wants to use, and then connect to the outside world with that IP and port. Then it gets the response, and then it talks to you through TCP. It says, hey, over your IP and port, here's the information that server sent back. But when you're inside your network, you don't necessarily know or care what that public IP and port are that you're using to communicate to the outside world. So a stun server is in the outside world. You're going to say, hey, stun server, I'm behind a NAT and whatever. I'm on this complex network, which has a bunch of infrastructure and stuff. Can you tell me, when you got this request, can you tell me what the IP and port are for that? And it's going to say, yep, here's your public IP and port. And we're going to keep that connection alive. Actually, I shouldn't even start this sentence because I forgot exactly the logistics of how this works. But it's going to keep that connection alive and redirect the endpoint to not be the stun server, but to eventually be the peer. So the NAT doesn't have a chance to choose a new port for a new connection. We're actually going to save that connection and redirect it to the other client. So that's what the stun server's doing for us. It's letting us know our public port and IP. And finally, a turn server. This one we're not going to use at all. Our turn server, traversal using relays around NAT. I don't like this one, personally, and we'll see why. This is optional. You don't need this, but sometimes you're behind a particular firewall or a NAT, which isn't going to allow a peer-to-peer connection. Maybe you're working for a company that blocks like all kinds of stuff, all kinds of different access, or you have a NAT that's really that's hiding your. Let me not even go down that sense. But you have NATs and firewalls that just won't allow you to connect to another peer. It's just not going to let you. Won't work. In that case, you need a turn server. And what a turn server is going to do is relay the actual stream between two clients. Where the signaling server is just relaying the messages to establish the stream. And once the stream is established, the signaling server steps out of the way and doesn't have anything to do with the actual connection between two clients. A turn server is right in the middle of that connection between two clients, taking all of the video and audio or whatever else you're streaming over WebRTC. You send it to the turn sends it to the other client sends its information to the turn sends it to the other client, and you're effectively just communicating through a server at that point, which for me just defeats the whole purpose of peer-to-peer if you're using a turn server. I don't know what the application is, why somebody would want to set up WebRTC and then use a turn server. Maybe there's a good reason out there somewhere. But for me, it just defeats the whole purpose. If you're going to use a turn server, why not just hop on a Zoom call? You're not peer-to-peer at that point, which is really, in my opinion, the point of WebRTC. But this does exist. It's a thing. So we talked about it. A reminder, you're only implementing the signaling server. All right, any questions? Are you in control of how many nodes there are? They have to be the last node to see the site or the first node to see what's next. Yeah. Yeah, so if there is one node. So have you, where do you configure that, how many nodes you have? Are you sure it's configured properly? Have you gone into that part? If you just download Tor and use it, it's probably not something you've looked into, how you're controlling the number of nodes. And even if you do have it configured properly, how do you know that everything is working the way you expect? The whole use of Tor, we can talk about privacy and stuff, but it's used for a lot of shady shit. The people running the network might be shady. How do you know that all that software is doing everything that it claims to do? It would be my caution. It would be more of my opinion on that. So even if I have it properly configured to have 1,000 nodes, how do I know that's what's happening? How do I know all 1,000 nodes aren't controlled by the same organization or the same person, for that matter? They might all those nodes might be running on the same server. I don't know. Yeah.
If there's a bunch of people on the server, how does the client know to send an offer to everybody? Or does it send one offer and then that one offer goes to everybody?
For application objective 3, you'll have to code that. So application objective 3 does get a little tricky. That is a bit more of a challenge, and you'll have to modify the front-end JavaScript to set that up. But so say there's a video call with 3 people in it, and a 4th person wants to join. That 4th person would send their offer to all 3 people with 3 different WebRTC connections. So you'd have to modify the JavaScript on the front end. I'll have more details on Friday especially. But in the front-end code, there's a line that says new WebRTC connection. You would have to call that 3 separate times to create 3 separate connections, and then create an offer with each of those 3 and send the offer to the 3 other peers. And your signaling server would have to route those messages depending on who it's for. So it does get more complicated. Application Objective 2 isn't too bad because you can assume there's just 2 connections. You just send it to the other one. Application Objective 3 is a little bit trickier. We can talk about it throughout the week. You saw something about the government having control of a bunch of nodes to see what's going on. I wouldn't doubt it. It seems like a thing the government would do. So if you set your number of nodes to 10 and the government controls 100 nodes, even if everything's random, all 10 might be, there's just a lot of, it's just a lot of shady stuff happening. So you gotta be on your toes and be careful with it. Yeah. Yeah, so that's why we reuse the connection when we talk to the turn. And again, I'm a little fuzzy on the details with this one. I had to talk to Oliver to see how this actually works. And I forgot, that was a semester ago. But it establishes a connection with the stun server, and then redirects, instead of keep staying connected to the stun server, it keeps this whole connection alive. So to the NAT, you're still talking to the stun server. It doesn't know that you're changing the target of that. But then we take that connection and switch it over to the client. So to the NAT, nothing changed. We're just using the same exact connection. Port forwarding I'm assuming you know, but for everyone else, port forwarding is the other solution to this, where you want to say, hey, I'm listening to connections on this port and this IP address. And then when your NAT gets a message over that port, you set up your port forwarding to say, hey, any messages over that port on our IP address, can you send that to my device that's running my Minecraft server? And then it'll be forwarded to your device. And you can handle that by running, the server can do what it's doing with that. So we could do the same thing, like WebRTC couldn't, but could potentially set up the same thing that says, hey, the WebRTC port is this port number, and then everyone can set up their port forwarding to their WebRTC devices. But then you wouldn't be able to have two connections with two different peers, where a server is listening, just like our web servers, you listen on one particular port, and then everybody connects to you on that port. With a WebRTC connection, you need a port for each connection, because you need those connections to each other peer. So that's why we don't use port forwarding here. Okay. Any other questions? I was trying to remember this as I was saying it. 6 to 20 milliseconds. Yeah, that's not a lot. You don't have a lot of time. So once you get, because I knew there was some limit, once it gets above a certain amount of lag, it's very difficult to communicate with another person. 6 to 20 milliseconds. So once you're over 20 milliseconds, communication becomes very difficult. That's well, as Argo said, that's tight. UPnP. I always forget what UPnP is. Sorry, I can't answer that. I see the acronym. I come across it all the time, and every time I look it up, I'm like, oh, yeah, that makes sense. And then I forget immediately what it is. Sorry, I can't help you on that one. Let's do the Promise WebSocket demo. And if this spills over to next lecture, that's fine. We got plenty. Friday's a demo catch-up code day, so we'll have time this week. WebRTC, I shouldn't even close my tabs. Probably on my clipboard. Hey. All right, let's chat. Hello. So the WebSocket stuff is the chat app portion of this. A few things I want to show. I might have showed this already, but it might be worth repeating anyway. If you go to your network, I have to refresh anyway. Hey, how come my chat history didn't show up? I'm showing bugs in lecture. If you go to your WebSocket and go to messages, you can see all of the back and forth on your WebSocket. So I received a message. Well, this is, if you want a cryptic hint. This is my part of my AO3 code. So you won't have that one unless you design it similarly. But I sent a chat message with hello, and I received a chat message, username, and hello. This is how we want our WebSockets working for objectives 1, 2, and AO1. And if we hop over to my server, I'm printing out my WebSockets. I do recommend doing this. That's a WebRTC WebSocket. Let's get to one of the messages, a little more maintainable here. So here, I received this message right here. I do recommend printing it out like this. I showed briefly one lecture how to print out bytes like this. It's actually right here still. I have this binary to string method where I take a byte, I remove the first 2 characters because it's always going to start with 0B, I think, to indicate that it's binary. And Python will remove the leading zeros, so I add in the extra padding, the leading zeros. And then when I'm printing these, I print 4 of them, and after every 4th one, I print out a new line, just so it's in the same structure as we're used to seeing on the slides. So I'm printing out my frames like that when I get bytes from the TCP socket on a connection that's been upgraded to a WebSocket connection. And we can make sense of these 1s and 0s. So let's do exactly that. Let's make sense of what these 1s and 0s are. And hopefully, well, we'll see how far we can get. So the fin bit is 1, so I know that this is just 1 frame for the message, or it's the last frame of the message more generally. My reserve bits are all 0s. My opcode is 0001, so I know that this is text data being sent. My mask bit is 1, so I know that this is a masked message, masked payload. My payload length is not 126 or 127, which would be all 0s and a 1 or all 1s, or all 1s and a 0 or all 1s. It's neither one of those. So this is my entire payload length, which we could do the binary stuff, but I know it's going to be 47. Then I'm going to have 4 masking bits, or 4 masking bytes, and then the payload. So since my payload length was only the 7-bit payload length, the 16-bit and the 64-bit, those things aren't present here. I know that this is my masking key, and I can start XORing this byte with this byte to get the first character, this byte with this byte to get the second character, this byte with this byte, etc. And then it repeats this byte with this byte until